So today I'm going to talk about rational trigonometry, which you hopefully have heard about, but if you haven't, you'll learn a little bit about it. We're going to talk about triangle geometry in a rather general setting, and then particularly interested in the in-center hierarchy of a triangle. So the outline of the talk is we'll start with some basic notions of rational trigonometry, and I'll talk about geometry with general bilinear forms. So it's a rather general approach to metrical geometry. And then we'll, in particular, look at three planar geometries called blue, red, and green. Blue geometry is just the ordinary Euclidean geometry, and while red and green are two relativistic geometries. And these three geometries sort of fit together in a beautiful way that's called chromogeometry. And then we'll talk about triangle geometry and standard coordinates. It's a very big subject, but we sort of have a new point of view on it. And in particular, we're interested in the in-center hierarchy. So we'll talk about that. We'll talk about fourfold symmetry and some perhaps remarkable strong concurrences that arise. So the last two topics are joint work with my graduate student, Nguyen Lê. And the main reference is this paper, which has just recently appeared, called Generalized Triangle Geometry and Fourfold In-Center Symmetry, and it appeared in COG last year, which is arguably the world's most beautiful math journal. Let me give you some evidence for that. So this is the recent edition, okay? And it's a color journal, has lots of color diagrams. The beauty is enhanced by George Glaser's wonderful photographs on the covers. So it's the Journal of the Croatian Math Society. Well, I guess that's the most recent one. Anyway, have a look if you're interested. All right, so let's start with some basic rational trigonometry. So this is an alternative to the trigonometry that you're used to, and it's a much better alternative, okay? So what we're going to do is we're going to start with a two-dimensional vector space and a symmetric bilinear form, which you can think of as like a dot product or an inner product. And the usual one is this one here that you all recognize, the dot product between two vectors, x1, x2 plus y1, y2. One can also introduce some variants, so I call this one the red inner product. It's a sort of a relativistic invariant with a minus sign instead of a plus sign. It's like a kind of a baby version of Einstein's relativistic framework. And then another relativistic geometry, this is really just another version of this one, but maybe a little bit different, called the green bilinear form. So we're going to start in general with a general bilinear form that's symmetric. Okay, that's our framework. And we're going to introduce some concepts. And the main concept is the concept of the quadrants of a vector. So we have a vector v, and we're going to define the quadrants of v to be v dot v. It's the simplest thing that you could possibly do. And we'll talk about the quadrants between points to be the quadrants of the vector joining those 2 points. Also the simplest possible thing you could do. We're going to make sure that we don't take any square roots, because I don't like square roots because they lead to irrational numbers, which I happen not to believe in. I know you all do, or most of you do, but maybe you'll change your mind someday. All right, but I don't believe in irrational numbers. I prefer rational numbers. This theory works over rational numbers, and in particular, the avoiding of square roots is very useful when we want to talk about these other relativistic quadratic forms, because otherwise we have to go to complex numbers and do more complicated things. All right, so in coordinates, this is what the quadrants between 2 points looks like. Just a familiar sum of squares, or maybe difference of squares. And in the green case, this perhaps somewhat unfamiliar product of differences. All right, so that's the quadrants between points, and we can now talk about the most important theorem in mathematics, which of course is Pythagoras' theorem. And here it is that if you have 3 points, A1, A2, A3, then A1, A3 is perpendicular to A2, A3, precisely when this quadrant's Q1 plus this quadrant's Q2 equals this quadrant's Q3. And here's a proof. All right. So using vectors v1, v2, and v3 for the sides, then Q1 is v1 dot v1, Q2 is v2 dot v2, and this hypotenuse will be v1 plus v2. So the right-hand side, Q3 is v1 plus v2 dot v1 plus v2. And we're saying that this is happening precisely when we have perpendicularity here which is given by the dot product in terms of the dot product of the two vectors being 0. That's what perpendicularity means for a general bilinear form. And I hope it's obvious that these two are equivalent. Because if you expand this right-hand side with the bilinearity, then the v1.v1s cancel, the v2.v2s cancel, and we have v1.v2 plus v2.v1, and we're assuming our quadratic form is symmetric, so that's 2 times v1.v2. And we're assuming that 2 is not equal to 0, so we can divide by 2. All right? So the equivalence works over a general field as long as the field is not of characteristic 2. Just a small point to keep in mind. Okay, I claim this is the world's most important one-line proof. Of course, there are dozens of proofs of Pythagoras' theorem. I think this is a very good one because it's short, it's sweet, and it's general. It's general. All right, let's have a look at how it looks like. So, of course, this is very familiar. This is the Euclidean situation, which I'm calling the blue one. And we have a triangle here. It's a right triangle. The meaning of the quadrances of the vectors can be just thought of as in terms of areas of squares. That's what you're doing when you take a dot product of a vector with itself. You're talking about the area of a square. And this is the way Euclid thought about Pythagoras' theorem. All right, let's look at something a little bit less familiar. The red version, the relativistic version. All right, so this is with respect to this red inner product. And here happens to be a red perpendicular triangle. That's a right angle there, because if you take the dot product of the vector 4, 2 with the vector 3, 6, 4, 2 dot 3, 6 is 12 minus 12, that's 0. And here you see the three parallelograms. These are actually squares. These are red squares. And the dot product is really calculating a signed area of this of these squares, and you see that indeed 12 plus minus 27 is minus 15. That's what Pythagoras is saying. Okay, there's also this green version where we're using the green inner product, this one down here. And here, the perpendicularity is manifested in a slightly different way. The easy way to think about green perpendicularity, and this will be important for the rest of the talk, so please pay attention, are that the perpendicularity is expressed this way. That if you have a vector like this and you reflect it in the coordinate axes, then you get a perpendicular vector. Okay? So this vector and this vector, this vector and this vector are perpendicular, because they're reflections essentially in that coordinate axis, or in that one there if you want. All right. So those are three green squares. This point here actually should be over there to make that proper. Sorry about that. All right. So Pythagoras works quite generally, and we're thinking we're onto something here. And here's the second most important formula in geometry, which is the triple quad formula. Much less familiar. It should be much, much more familiar. Okay, it's a statement about when 3 points form a collinear set. Not a perpendicular triangle, but a collinear set. So the statement is that if you have 3 points, then A1, A3 is parallel to A2, A3, precisely when this particular relation holds. Q1 plus Q2 plus Q3 squared is equal to 2 Q1 squared plus Q2 squared plus Q3 squared. Okay, the proof. In one way is easy. If the points are collinear, it's easy to see that this is satisfied. It's not so easy to see it the other way around. Okay, so we look at this expression, we rewrite it using an identity. We recognize that these things here in terms of dot products are these things here. This is basically the calculation that I did in the previous slide. And then one goes to coordinates. One chooses an arbitrary symmetric matrix to represent the bilinear form. Sorry. And one has coordinates for the vectors v1 and v2, and then one computes this quantity. v1.v1, v2.v2 minus v1.v2 squared, and it's a computation that you have to make. And gloriously, there's a lovely factorization, and you get this formula here. So if you're assuming that the quadratic form is non-degenerate, which we will be for this talk, this AC minus B squared, it's a determinant, that's non-zero. So this thing being 0 is exactly precisely equivalent to this thing being 0, and this is parallelism of the two vectors. this should be in most linear algebra texts. Okay? It's pretty fundamental. Because it turns out that this relation, this quantity, this difference is of major importance. Okay, so that's quadrants. The other important notion in rational trigonometry is spread between two lines, and it's defined this way. It's actually motivated by what we just did, because if you look at this thing here, you see the expression we were just fiddling around with. And so it's 1 minus v dot w squared over the quadrants of v, quadrants of w, for any two vectors, for any symmetric bilinear form. It's a rational replacement of angles that opens up so much of geometry. Okay, it generalizes geometry so much. In the Euclidean case, the familiar Euclidean case, it all becomes down to this. And you will recognize that this is the square of the sine of an angle between the two lines. Okay, so spread is sine squared of an angle if you happen to know what angles and sine are. But if you don't happen to know, because this is all relatively elementary, we can get at the notion of angle through this purely rational, very simple high school kind of concept. So together with quadrants and spread, these are the foundations for rational trigonometry, and we can lay out metrical geometry in a new and exciting way with many, many new directions and implications. Okay. Here's a spread protractor that you can find online. It's quite a pleasant thing. Of course, not linear, right? Spread is not linear. It goes from 0 to 1 and 1 to 0. Okay. I might just quickly mention that this formula for the spread can also be interpreted as the ratio of a determinant, essentially a normalized determinant. You're taking the determinant of the area of a parallelogram and normalizing by dividing by the quadrances of the sides. You're squaring it so that it's symmetric and so that it doesn't depend on the order. And then here are the three main laws of trigonometry that follow. In about 20 minutes, if I had 20 minutes, I could prove these formulas from the definitions that I've just given you, requiring no transcendental notions, no irrational numbers. This is the analog of the cosine law. This is the analog of the sine law. And this is the analog of the fact that the sum of the three angles of a triangle add up to, let me think, 3.1415926. How does it go after that? But there's some very, very complicated number that the angles add up to. But this is the much simpler algebraic replacement of that transcendental fact. Notice that if we remove this interesting cubic term, we're back to essentially the triple quad formula. Okay.
Sorry, the only thing you're assuming here is symmetric, non-degenerate.
Symmetric, non-degenerate. Yeah. Yeah, so in particular, the geometries that you can build here include, for example, geometries that operator algebraists might be interested in. Trace x times y. That's a symmetric bilinear form that works in the world of operators. It's generally not positive definite, but it has a geometry that's just as rich as the Euclidean one if you look at it from this point of view. Or if you've done Lie theory and you know about the killing form on Lie algebra, trace of add x, add y, it's another similar kind of story, usually not positive definite. But with these tools, we can access these things and think about them geometrically. Okay, now a few quick introductions to some triangle geometry. Okay, this is Euclidean triangle geometry. Here we see the Euler line. We see the centroid, which is the meet of the lines joining vertices to midpoints. We see the circumcenter, which is the center of the circle that passes through the 3 points. We see the orthocenter, which is the meet of the three altitudes. And as Euler realized, these 3 points lie on a line, and they form the relation 1 to 2. And of course, this is just the start of triangle geometry. It's gone much, much more now, and encoded in Clark Kimberling's lovely Encyclopedia of Triangle Centers, which is online, has more than 5,000 listed triangle points. Okay? So the orthocenter is the fourth one in his list. The centroid is number 2. The circumcenter is number 3. The 9-point center, which is the center of the circle passing through the 3 midpoints, is X5, and so on. There's another 4,900 or at least points that have been cataloged and studied. Okay? So we know more about a triangle than we know about anything else in mathematics, for sure. Okay, it is very deep, and it's becoming realized that it's not elementary either. It's very, very complicated. Once you get down to a certain level, it becomes very, very rich. And you'll perhaps see some of that today. Okay, here is the red version of that. Okay, same triangle, but now with respect to red perpendicularity, it turns out that the 3 red altitudes meet in this point. The centroid is just as it was before. The 3 perpendicular bisectors meet in this point, which is the center of the red circle that passes through them. What's a red circle? Well, it's something of the form x squared minus y squared equals k. So it's a rectangular hyperbola, either like this or like that. There it is right there. Lo and behold, the 3 points line up just as they do in the Euclidean case. So that was something I proved maybe 5 or 6 years ago. I'm not sure if it had been noticed before that. Okay, here's the green version, which is very much the same story, except that now the hyperbolas have asymptotes which are parallel to the axes.
So the red and the green are the same after coordinate change?
After coordinate change, the red and green are the same. But as this diagram shows, if you study it carefully, the blue, red, and green, it's important to keep them separated. Okay, so this is a remarkable thing, which I call the omega triangle. Here's the same triangle that we were studying. I basically superimposed all 3 of the previous diagrams. We see the blue orthocenter, the green orthocenter, and the red orthocenter forming what I call the omega triangle of the original triangle. And remarkably, the red circumcenter is the midpoint of the blue and green orthocenters. And similarly for the other things. And the 3 Euler lines, all passing through the centroid here, are the blue one, the red one, and the green one, are just the midlines of this triangle. So the 2-to-1-ness that Euler discovered is just the manifestation of the familiar fact that the midlines of a triangle intersect each other in ratio of 2 to 1. And there are quite some other remarkable things that you notice that, for example, the green orthocenter lies on the blue and the red circles, etc. So this is chromogeometry. So it's something that becomes visible when we allow ourselves to think about more general bilinear forms. In particular, relativistic forms together with Euclidean ones. Okay, now I'm going to talk about joint work with Nguyen. Okay, and we're going to talk about triangle geometry with general bilinear forms. So our strategy is, all right, we've got all this beautiful triangle geometry out there. Let's study it using rational trigonometry. And we have a very basic idea, which is just motivated by this change of variables. Okay, so we're working in a linear algebraic setting, and suppose we have a bilinear form represented by this big circle, the big circle. And so there's a symmetric bilinear form. B is some invertible symmetric 2-by-2 matrix. And suppose we're interested in a linear change of coordinates. So phi is a linear transformation given by some invertible 2-by-2 matrix M. And we're thinking of our vectors as being row vectors so that the M would act on the right-hand side. All right, so we can use that linear transformation to convert the original bilinear form to a new bilinear form. Right. So in other words, we can define a new bilinear form W1 dot W2 by essentially what the images, the pre-images of W1 and W2 were, what their inner product was back in the original. So if we invert by the inverse and then apply the original bilinear form, we get a new bilinear form. So the change induced by linear transformation on the space of forms is given by this kind of transpose conjugation, as students of linear algebra learn. All right. So All right, that's very good. So we're going to do, we have the following idea. It's very simple, okay, but it turns out to be remarkably powerful. So our idea is that we want to study a triangle. Wouldn't it be nice to use linear algebra and transform that triangle into some very simple triangle? Say the triangle whose points are 0, 0, 1, 0, and 0, 1. Right? So we can do that by first translating so that one of them is at the origin, and then we make a linear transformation. So now the triangle has been linearly transformed to this simple triangle. Okay. So why don't people who do geometry do this? Well, it's because the bilinear form that you're considering, usually the Euclidean one, changes if you do that. It changes. It changes exactly in the way that we've just discussed. But that doesn't bother us because our technology works for any bilinear form. So that's good for us. So what we're going to do is we're going to transform our given triangle to this standard triangle, and whatever bilinear form you started with has now been transformed to this one. This is a general bilinear form. So I don't care whether you're starting with the blue one or the green one or whatever. You've changed your triangle with this transformation. You now have this form. So now we're in a position of studying this particular triangle with this general quadratic form. We changed the emphasis. Instead of studying a general triangle with a particular quadratic form, usually the Euclidean one, we're studying a particular triangle under a general quadratic form. So the variables are A, B, and C, the numbers appearing in this bilinear form. We're going to assume that this is non-zero, so the determinant is non-zero. And it turns out that this quantity here, what I might call the mixed trace, maybe somebody can tell me what another name for it, but it's A plus C minus 2 minus B plus B. Okay, that turns out to play an important role, so we're going to call that D. All right, so the ingredients are A, B, C, and D. And we're now going to do triangle geometry on this triangle, which is really encoding a general triangle in a general inner product space. So what we can do is we can determine the quadrances of this triangle and the spreads of this triangle. We just apply the formulas, right? So for example, if you have a vector 1, 0, that's one of the sides. To find the quadrants, you have to take that vector dotted with itself. It means you have to multiply 1, 0 times the matrix A, B, B, C times 1, 0 transpose. And you're going to get A. So those are the three quadrances, and then here are the three spreads. And here are the 1 minus the spreads, which are also important. So they turn out to be this. They're important because of the following theorem. That when you have two lines and you're interested in bisecting them, that bisector exists precisely when a number theoretic condition is satisfied. Precisely when 1 minus the spread is a square in your field. Okay, we're working over a general field here. Could be the rational numbers, could be a finite field, could be the complex numbers, or even the real numbers if you really believe in them. All right. Okay, so the 1 minus the spreads encode when we have bisectors. And so because the numerators here are already squares, we see that the existence of bisectors comes down to whether AC is a square, whether AD is a square, and whether CD is a square. So we're going to assume now that those conditions are satisfied. That we have a U, have a V, and have a W satisfying AC equals U squared, AD equals V squared, and CD equals W squared. That will guarantee what we usually call angle bisectors in this story. Okay, there's some flexibility here because if you have U, then you can just replace it with minus U. So we can choose things so that ACD is equal to UVW, and then there's sort of these quadratic relations that fall out from these formulas. So we're augmenting A, B, C, D now with three more numbers, U, V, and W, which are some kind of algebraic square roots of these three combinations. Okay, now I can show you pictures. Okay, so what happens? Well, let's first of all just establish a bit of notation. If we have a line in the plane given by equation AX plus BY plus C equals 0, we're going to abbreviate that to just the proportion A to B to C. That encodes the information of the line. Okay, our first theorem is that the points H, C, and G, which are the orthocenter, circumcenter, and centroid, are concurrent. No, not concurrent. I should have written collinear. These are points, not lines. So the statement is these 3 points are collinear. That means they lie on a line, and they satisfy this affine relation. And moreover, the formula for the line that they lie on is this one. It's a formula involving the determinant, that's the delta, was the determinant AC minus B squared, ABC. Okay, the proof, well, is a calculation, as most things turn out to be in this subject. You have to calculate the centroid, you have to calculate the orthocenter, you have to calculate the circumcenter. And you do that because you know what the midpoints are and because you can calculate perpendicularity from the bilinear form. Okay, and once you have these, then you can easily determine that this is the line that passes through those points. So notice we have now proven that in any metrical geometry, these 3 points always exist and that they are collinear. I told you before that it was true for the blue, red, and green geometries. I'm now telling you more. I'm telling you that it doesn't depend on which matrix you choose. Choose any old matrix, you have any geometry, there will be an Euler line. But we're really interested in the in-center story. So we're going to assume that we have these in-centers given by these bisectors. And here are the formulas for the bilines. So these are actually the lines that bisect our triangle. We have our standard triangle, 0, 0, 1, 0, 0, 1. A bilinear form. These are the formulas for the bilines. And then we can check that these bilines meet 3 at a time in the 4 in-centers. So there can be 4 in-centers, and here are their formulas. In terms of U's and W's, and then sort of alternate, more simple formulas with some D's. So even in Euclidean geometry, there are really 4 in-centers, but the 3 of them are usually called x-centers, and usually only one is called the in-center. That's x1 on Kimberling's list, the in-center. And it's a very interesting and good choice, I think, for the first of all the triangle points, because the in-center is really interesting, and the stuff that comes out from this in-center hierarchy is really fascinating. Okay. So what does it look like? I am now going to show you things in the green geometry. Okay? The Euclidean geometry is too familiar. I want to convey to you that relativistic geometry is interesting and worth studying. Okay? As Einstein probably would want us to think. It's been more than 100 years, but relativistic geometry as a subject in geometry hasn't really been developed that much. So here's a relativistic picture of the green story. Here are the bylines. So that's one byline. I call it the same as an angled bisector. Right, there's 2 of them at each vertex, and they meet 3 at a time at the 4 in-centers. There's one there, one there, one there, and one there. And these in-centers are the centers of circles which touch the 3 sides. The circles in this case are rectangular hyperbolas. So for example, the circle, the in-circle associated to that in-center is, what did that little thing go on? Is this one here. Okay, it touches that side, touches that side, touches that side. There, you can see 4 in-circles. Notice that the places where these in-circles touch the sides, we're going to call those contact points. Okay, there's one there, one there, one there. There's 12 of them. All right, if we join points with contact points, we join, that is with the vertices of the triangle. So we join the vertices to these contact points of the in-circles, then those lines meet. They have nice concurrences. They meet in essentially 4 Gergon points. If you look at the lines associated to one incenter, so it has 3 contact points, and you join each contact point with the opposite vertex, those 3 lines will meet in a Gergon point. And there are 4 Gergon points, because there are 4 incenters. Okay, so here's now a theorem that the lines joining corresponding Gergon and incenters are Soddy lines, that's what they're called in Euclidean geometry, and they meet at the de Longchamp's point. There's our first example of 4-fold symmetry, or a strong concurrence. Okay? So what we're saying is that, so this incenter is, its Gergon point is that one there. This incenter has Gergon point there, this incenter has Gergon point there, and this incenter has Gergon point there. And when we connect each incenter with its corresponding Gergon point, the 4 lines that we get miraculously concur. And the point with which they concur is the de Longchamp point, which, and here is its formula in terms of our coordinates. It turns out to be the orthocenter of the double triangle. The double triangle is the triangle that you get by drawing parallel sides to the 3 triangles, to the original triangle parallel to the other sides. So it's a bigger sort of 2-fold extension of the triangle. All right, so that's an example of a strong concurrence. Okay. Now, there are some other points associated to these lines joining joining vertices to contact points. So there are some other 4 points. If you look at all those lines joining vertices to contact points, you see that there are some other places where they're collinear. For example, there was our Gergon point, but there are these other ones which are called Nagel points, and they're N, and maybe somewhere down there. And if you join each incenter with the corresponding Nagel line, then they meet in the centroid of the triangle. Okay, so these lines that, say this one here, that pass through an incenter, a centroid, the centroid, and a Nagel line are some kind of analogs of the Euler line. Okay? They're called Nagel lines in Euclidean geometry, and they've been very well studied. And it turns out that this ratio, the ratio of this to this, the ratio of Ig to Gn is also 1 to 2, just as in the Euler line. Okay? So there's some kind of correspondence, but there's 4 of these Nagel lines, while there's actually really only 1 Euler line. The 4-fold symmetry applies to everything that you build up from the incenter. Okay, so we've got these 4 incenters. Each of them has an associated Gergon point. Each of them also has an associated Nagel point. We've joined the incenters to the Gergon points and the incenters to the Nagel points and found some strong concurrences. What about now joining the Gergon points to the corresponding Nagel points? They're also in correspondence, so we can join them up. And that's what we've done in this diagram here. And we see, remarkably, that we get another strong concurrence. 4 lines meeting in a point. This point, called x20, is, no, it's not x20, it's x69, sorry. This is something to come. x69 is where these Gergon-Nagel lines meet. And that is the isotomic conjugate of the orthocenter. I'll explain what that is in a second. But here's the formula for it. Okay. So what we are doing here is for every point, every construction has associated to it a formula. And we want to know what that formula is. Once we have that formula, it's then an ingredient in future formulas. And allows us to really explore the relationships of all these things that are happening. So it's a very analytic approach to things, but it's a very general analytic approach because we're working with a general triangle over a general quadratic form. All right, what does this isotomic conjugate mean? Well, there are two standard, very important kinds of conjugates. I talked about this about a year or so ago in the context of hyperbolic geometry, but I'll tell you again. So there's something called an isogonal conjugate and an isotomic conjugate. So if you have a triangle, A1, A2, A3, then, and some arbitrary point x, then you can join the arbitrary point x to the three vertices of the triangle and get three lines. And then if you reflect those three lines in the angle bisectors at each vertex, so you reflect the line A1x in the angle bisector at the vertex A1, what I call the biline, you get another line. So from these original three lines through x, you get three new lines that are obtained by reflection. And remarkably, those three new lines meet in a point, which only depends on x. And that's called the isogonal conjugate of x. That was one of the major discoveries of the 19th century triangle geometry that propelled a lot of investigations. This idea that there was this isogonal conjugate, and you could, if you had an important point, you could take its isogonal conjugate and you got another point. All right. So now there's a variant to this called the isotomic conjugate. What you do is you take a point x, you look at these three lines, A1x, A2x, A3x, and you see where they meet the opposite side of the triangle. So they meet, each one of these meets the opposite side of the triangle in a point. And you reflect that point in the midpoint of that opposite side. Okay? So you have these three intersection points. You reflect each of them in the midpoint and join up again to the original vertex. When you do that, then the three new lines also meet in a point, and that's called the isotomic conjugate. All right, so we're in a position to calculate these things, and so now we can assert that these are general facts. They're not just facts that hold in Euclidean geometry. They're facts that occur in general geometry. In a relativistic geometry, there are isogonal conjugates. There are isotomic conjugates. And here are the formulas for them. So given a point x, y, here's the formula for the isogonal conjugate. Here's the formula for the isotomic conjugate. Notice that this one doesn't involve A, B, and C because it's a purely affine notion. This one does involve A, B, and C. It depends on the metric. So that x69 that I was telling you about in the previous one, that's the isotomic conjugate of the orthocenter. That's the definition of x69. That's also the place where these four Gergon-Nagel lines are meeting. Oh, sorry, wrong way. Okay, so some more interesting points called Bevan points. And they're obtained by, again, looking at these contact points that we started out with and joining them to the incenters now, not to the vertices, but to the incenters themselves, which is the same as dropping perpendiculars from the incenters to the three sides. So we draw perpendiculars to from an incenter to the three sides. We get these three altitudes for each incenter. Where's the other incenter? Down here. And then these 12 lines meet in some new points. They're called Bevan points. Okay, in our paper we mistakenly call them new points, but they're not new. It's hard to actually discover new points because Kimberling's list is so exhaustive. But anyway, so they're called Bevan points. And what we discover is that if you look at the lines joining corresponding incenters and Bevan points, the in-Bevan lines, that they all concur in the circumcenter. Another strong concurrence. Well, the next ones are having to do with the Mittenpunkts. So the Mittenpunkts are points that are obtained by joining incenters to midpoints of the opposite sides. So if you join an incenter to the midpoint of the opposite side, you get 12 new lines, and you look at those new lines, maybe a little bit complicated here in our example, but in any case, you see that those lines are concurrent in 4 new points called the Mittelpunkts D. 1, 2, 3, 4. And then our theorem is that the in-mitten lines, so the lines joining in-centers and mitten points, are concurrent, and they meet at the symmedian point. It's a new point. That's actually a very important point. It's x6. And there's a formula for x6. Its definition is that it's the isogonal conjugate of the centroid. The symmedian point is the isogonal conjugate of the centroid, and it generates a lot of interesting triangle geometry. Okay, so here are now here are some of the points associated to just one in-center. So I'm going to sort of strip away a lot of the fourfold symmetry and just show you sort of one of the pictures. So if we start with, say, this in-center, then its associated Gergon point is this G here. Its associated Nagel point is down here. Let's see, the centroid is always the centroid. That's just an affine notion. The Bevan point here. There's the D, the Mittelpunkt. This point here, it's called the Spiker point. That's X10 or something. And it's the midpoint of NJ and IJ. This is a Nagel line that I said was analogous to the Euler line. So the Spiker point is analogous to the 9-point center on the Euler line, halfway between the circumcenter and the orthal center. Here for reference is the Euler line, which you would think wouldn't have that much to do with these in-centers, but the Euler line has to do with all aspects of triangle geometry. And so it's not entirely surprised that this X20 that we discovered also lies on the Euler line. In fact, it's the reflection of the orthal center in the circumcenter. There are some other nice sort of ratios here. Nguyen, you can correct me if I'm wrong. I think this is in the ratio of 1 to 2. And maybe, I can't remember. Oh, this one here, notice these ones line up. And I think this one is the midpoint of those two. This one is the midpoint of those two. Are there relations along here too? We don't know, okay. Anyway, you can see that it's rather a beautiful picture, right? There's lots of these interrelated things. And as you explore triangle geometry, you have this feeling as if you're just discovering more and more pieces of the jigsaw puzzle that are somehow miraculously fitting together. So I guess what we have here now is a technology for thinking about triangle geometry, because we have a way of analytically pinning down all the points. And we have a way of generalizing these results to a much wider setting, including a relativistic setting. Here's a summary of the strong concurrences that we found involving the in-centers, Gergon points, Nagel points, Mittelpunkt, Spiker points, which I haven't said too much about, and the Bevan points. Okay, and here they are here, and so you can see where the corresponding lines meet in a fourfold way. And you see that it doesn't always happen. It's not automatic. Okay, so for example, the Gergon and Spiker, you join those points up, you get 4 just random lines, seemingly random. So it's not just an automatic thing. It's something that requires work, case by case, to discover and to prove. So it turns out that this is just the tip of an iceberg, okay? That there are many, many more examples of fourfold symmetry and strong concurrences that are sort of built on this kind of thing. And Nguyen will hopefully be reporting about that more in a future talk. I want to end today with a quite spectacular thing, I think. Maybe I will motivate that by going back a little bit. Okay, so here's our green triangle again, and here are the 4 incenters. There, I'll remind you, there's one there, one there, one there, and one there. Can anybody see something that's sort of interesting or novel about those 4 points?
They all lie in a circle.
They all lie on a circle, right. Those 4 points form a cyclic quadrilateral. But it's a blue circle, right? So when we say circle, we mean blue circle. Well, it turns out that those 4 points also lie on a red circle. And so this is I think, quite mind-blowing to me, okay, this theorem. It says that if you have a triangle, and for illustration purposes, the triangle is now very thin and small. So the triangle is just A1, A2, A3. Okay, but it's small so that we can see all the incenters. I've shown you here now all 4 blue incenters, all 4 red incenters, and all 4 green incenters of this triangle. The 4 blue incenters are here, 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 and here. 4 green ones are here, 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 and here, and the 4 red ones are here, 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 and here. And the theorem says that the 4 red incenters and the 4 green incenters lie on a blue circle.
So what's the definition of circle?
So a circle is just given by the quadrants to a fixed point being constant. Quadrants in terms of v dot v.
So is the center of that circle got rational coordinates?
Well, so the center of the circle is the blue orthocenter, h sub b, so yes it does. If the original triangle has rational coordinates, that will move too. And similarly for the other colors. So the 4 green ones and the 4 blue ones lie on this red circle, whose center is the red orthocenter. And the 4 blue ones and the 4 red ones lie on this green circle whose center is the green orthocenter. Remember earlier I showed you that complicated picture of the omega triangle? The omega triangle was the triangle formed by these 3 orthocenters. So here we see another manifestation of chromogeometry that these 3 colors want to interact. They want to be considered all 3 at the same time. Okay, so in terms of references, more information, well, there's my book on rational trigonometry. There's some articles on chromogeometry, and the main article supporting this lecture, which I've mentioned, Nguyen Le and myself, that appeared in COG. Also on my YouTube channel, there's various YouTube series. There's a Wild Trig series that teaches you all about rational trigonometry. There's universal hyperbolic geometry, which teaches you about universal hyperbolic geometry. There's a previous lecture from last year on hyperbolic triangle geometry. And I want to mention sort of work in progress, a computer program that's being developed by Michael Reynolds, who you heard last week, talking about the 4-color theorem here. Okay. So Michael's a busy fellow. He's not only working on graph theory and rounding up criminals, but he's also working on a large-scale program to implement rational trigonometry, chromogeometry in a very general setting that will allow sort of very explicit computations for triangles and incenters and all kinds of interesting points. So I think that'll be a very interesting development. So I just want to sort of finish by saying triangle geometry has had a very, very up and down history. There have been times when it's been very intensively studied, and then there have been times when it's been relatively dormant. It's now on the up and up because, especially with the dynamic geometry packages that we have now, with Geometry Sketchpad, CAR, Cinderella, GeoGebra, people now are starting to investigate, and amateurs can delve in, roll up their sleeves, get out one of these programs, and start playing around and discover things. And it's becoming clear that this subject is so vast and intricate and complicated, and the further down you go, the more and more lovely, incredible things that are waiting to be discovered. So I think it's going to be a sort of a major driver of 20th century geometry, this triangle geometry. So maybe some of you can get involved too. Thanks for listening.